A pale cocoon swims up from the deep sky and exhales. Jets whisper from its sunlit skin. The coma brightens, the shape sharpens, the night around it seems to lean in. Yet the track through the stars hardly twitches at all. Breath without sway, motion without shove. 33 trillion kilograms as a lower bound, and a push so small it drowns in the noise. Stay with this, because the simplest answer points to something vast, and the strangest answer is not the one you think. It begins with a number that does not behave. 33 trillion kilograms, a careful lower limit, not a boast. Astronomers watch a visitor from between the stars, and they see the unmistakable signs of activity. Sunlight warms, buried ice. Vapor slips free as thin jets that glitter in backscatter. In the language of comets, this should mean a measurable nudge, tiny but real, a whisper of rocket force that leans the path off a perfect gravitational arc. Instead, weeks pass, then months, and the orbit looks almost ideal, as if the jets were stage smoke. The mismatch feels like a finger tapping the glass. Something here is heavier or stranger than it first appears. Look at the object itself. In Hubble images, it wears a teardrop glow, a soft brightening toward the sun that makes professionals squint. Most tails stream away from sunlight, shaped by radiation pressure and the solar wind. This forward glow hints at larger grains and strong forward scattering, a signal that dust and light are not playing by beginner rules. The visual tells the same story the spectra tell. There is vapor. There is dust. The coma is alive. Activity is not in doubt. Now set the visuals beside the measurements. Over 4 months, a global web of telescopes stitched together 4,022 precise positions. Each point is a small promise to the next, where gravity alone would put the visitor, where it actually lands in the field. The difference between those two is the non-gravitational shove. In this case, that difference shrank toward nothing. Limits tightened until the allowed acceleration sat in the realm of billionths of a meter per second squared. That is not a poetic phrase, it is an accounting line. A ceiling on any hidden push that the jets could supply. So what bridges breath and steadiness? Momentum makes the rules. Gas escapes at a few hundred meters per second. Multiply by the mass that leaves the surface each second, and you get a recoil that should move a small body. If the measured acceleration is near zero, and the outflow is not trivial, then the mass that absorbs that recoil must be large, not infinite. Just large enough that the same push produces a drift too small to see. Imagine tossing tennis balls at a freight train. The balls carry momentum. They hit with small thumps. The train hardly notices. We are watching the space version of that intuition. There are other possibilities, and we will walk through them later with care. Perhaps the coupling between gas and nucleus is less efficient than assumed. Perhaps geometry and brightness structure tug the apparent center of light away from the solid heart, which could hide some of the recoil in the photometry. Perhaps the mass loss rates are smaller than first estimates suggest, though the visible coma argues against a very low number. For the moment, the straightforward path remains the big one. Weak push plus clear activity equals a heavy nucleus, a quiet giant that breathes and keeps its course. This is where the story asks for discipline. The claim is not that models are flawless. The claim is that the floor on mass is already high given the silence in the residuals. It is also a reminder that science is a process, not a proclamation. The analysis is preliminary, the inputs will sharpen as more teams publish, and the limit can move. But the paradox itself is robust enough to hold attention. We are used to comets that drift when they vent. We are used to asteroids that do not vent at all. We are not used to something that exhales like a comet and glides like a mountain. The next step is to pull back the curtain on how these claims are built. What kind of measurements place a leash on a force that small? How does a world-sized relay of observatories turn faint points into a law firm of numbers? And how do we know that we are not fooling ourselves with a pretty image or a convenient unit? Before we chase the chemistry and the strange glow, we need to meet the people and the practice that set the stage. Begin with a clock that spans continents. Night falls in Chile. A dome opens. The object steps a fraction against a fixed lattice of stars. Night falls in Hawaii. Another step. Europe. Another. Australia. Another. Each frame is a receipt, a record of where the visitor sat in celestial coordinates at a precise moment. Stack thousands of those receipts, and you get a ledger that tells a very simple truth. Gravity alone draws a clean curve. Anything extra would bend that curve by a hair. If the hair is not there, then any extra force must be very small. Astrometry is the craft of writing down those hairs. Telescopes take exposures that catch the visitor and dozens of reference stars in the same field. The stars are the yardsticks, bright and fixed. Software corrects for optical distortion, for atmosphere, for detector quirks that can drag a point a fraction of a pixel. Timestamps are synchronized to standards that are boring but sacred. Coordinated universal time, leap seconds accounted for, observatory clocks disciplined by radio and by fiber. Positions are solved in right ascension and declination, then folded into an orbit that is the best fit to the entire set. Outliers get flagged, systematics get hunted. Nothing mystical, only the patient shaving away of error. Over 4,022 measurements came from 227 observatories. That number matters less than the variety behind it. Large mirrors and small, professional, arrays and seasoned amateurs who know how to calibrate to within an arcsecond and better. Northern sky and southern sky. Different cameras, different filters, different weather. Diversity cancels local bias. When such a mixed chorus sings the same line, listeners lean forward. With an early orbit in hand, analysts test a simple model. If there is thrust from outgassing, add a term that points roughly away from the sun and change magnitude with distance, then see if the residuals shrink. Residuals are the leftover differences between predicted positions and measured positions. If adding a small push drops those differences, nature is hinting that the push is real. If the differences do not drop, set an upper limit instead. In our case, limits improved as the calendar turned. The ceiling on any non-gravitational acceleration slid into the realm of billionths of a meter per second squared. That is a mouthful. It means that over a full day, the extra speed added by jets would be less than the thickness of a human hair per second. If it were any larger, the thousands of positions would have felt it. Precision at this level survives only if you respect light. The visitor is not a hard point. It sits inside a soft cloud. The center of that cloud can drift as dust flares and fades. The fix is to model the coma itself. Observers vary exposure time to control blooming. They check different apertures to see how the centroid moves as you include more or less of the glow. They track changes with phase angle as the sun, the object, and Earth slide into new geometry. They compare visible light frames with infrared maps that trace gas more than dust. The goal is not perfection. The goal is to know how far the photocenter can lie from the true nucleus, and to fold that uncertainty into the fit. A parallel track watches the brightness over time. Photometry is less about position and more about the mood of the object. If jets wake up, the light curves show it. If the coma expands, halo widens, and the profile changes. Here again, the planet-sized relay matters. A gap in one place is covered by a night in another. The curve smooths out. That curve does not tell you the mass. It tells you whether mass loss is likely steady or spiky. That helps when you ask whether a sudden burst could hide a small shove that the astrometry missed. Spikes leave fingerprints. Gentle breathing does not. None of this work claims that outgassing is absent. Spectra prove that vapor is there. Images show the soft envelope. The question for astrometry is narrower. Given the vapor, how large could the recoil be without leaving a mark on the track? The answer is not very large. That in turn forces mass upward, if the outflow is anywhere near typical values for a comet that looks this active. A lower limit on mass is the clean product of that chain. It is not a declaration of exact size. It is the floor under the room where debate can walk around. This is why the paradox survives scrutiny. Measurements from many eyes tell a consistent story about motion. The coma and the spectra tell a consistent story about activity. Together they point to a heavy traveller that breathes. That does not mean imagination stops. It means imagination must build on the same ledger. In the next chapter, we will touch the physics that turns vapor into thrust, and we will see why comets usually drift when they exhale, and why this one seems to hold its breath without moving. Picture a garden sprinkler under a bright noon Sunday. Water leaps from the arms spin, and the push comes from the flow itself. A comet is a slow and colder version of the same idea. Ice inside the nucleus warms, molecules escape, and every escaping packet of gas carries momentum in one direction. The nucleus must accept the equal and opposite response. The textbooks do not need romance here. Forces change in momentum over time. Gas leaves quickly, the body responds slowly. Over weeks and months, the response adds up to a measurable drift. Begin with the ingredients that are easy to visualize. Think about a nucleus a few kilometers wide. The surface is porous. Sunlight strikes and warms patches that peek out of shadows. Water turns to vapor. Carbon dioxide turns to vapor even earlier because it is more volatile. The gas floods through microchannels. It bursts from vents. It carries tiny grains of dust that ride the flow like sparks in a campfire column. The flow speed is set by the heat and the microphysics in the surface skin. Hundreds of meters per second is typical. Even if the mass loss each second seems small to our senses, the momentum in that jet is stubborn. Multiply a modest mass flow by a fast speed, and you get a steady push. Observers do not need to drill the surface to know that such jets exist. They see them indirectly. A coma grows, lines in spectra brighten. The profile of light around the nucleus changes shape with the angle to the sunday. In familiar comets, the result is not subtle. The orbit solution that fits early data without any extra force starts to drift as the object grows active. Analysts add a parameter that stands in for jet thrust. The fit improves. The implied acceleration is tiny in daily life, but plain on a plot that watches months tick by. Nature signs the receipt. Comets that breathe usually budge. So why would a breathing traveler hold its line? The simplest way is mass. If a body is heavy enough, the same jet that could push a small nucleus into a detectable wiggle will only slide the heavy one by a distance too small for our instruments to separate from zero. Think about a child pushing a tire swing. A light tire creeps, a heavy tractor tire barely responds. Swap the playground for space, and the analogy still works. The gas carries the same momentum. The body soaks it up without obvious motion. There are other knobs to turn in the model. Not all gas momentum couples cleanly into a net shove. If jets fire from several regions, some of the pushes cancel. If gas emerges through a blanket of dust that collapses back, some momentum stays in local turbulence rather than launching into space. If grains are large, they carry momentum too, and that can change how push and glow relate. Engineers who model such flows talk about efficiency, meaning the fraction of escaping momentum that goes into a net thrust on the nucleus. When that fraction drops, the same activity can leave a smaller orbital trace. These counterpoints matter, yet they do not erase the basic arithmetic. For comets that look as active as this one, analysts can bracket plausible mass loss and gas speed using actual spectra and coma size. With those brackets, even a conservative efficiency still yields a recoil that should register if the nucleus is small. The measurements say the recoil does not register. The inference is a heavy nucleus, or something that hides momentum in a new way. The first option is simple. The second option is the outlier that demands proof. It is worth pausing on units because precision lives there. Non-gravitational acceleration is usually reported in meters per second squared. The limits quoted for this visitor fall around billionths of that unit. Over a day, such an acceleration would change speed by less than a millimeter per second. Over a month, the total positional shift would be small but still trackable for a small comet if the force persisted. Here, the tracking did not require such a term. The fit stayed clean without it. The jets are present. The shove is not. Reality adds texture. Jets do not fire at constant power. The nucleus rotates. The sun angle changes. The flow can be on for part of a day and calm for another part. Yet these variations tend to average out in long arcs. That is why multi-month monitoring is so powerful. Bursts and lulls smear into an effective value for the push. If the effective value is still near zero, the lesson is not fragile. It holds across chatter in the gas. The practical, the effect on our story is direct. A working picture forms. The object vents like a comet. The activity is strong enough to paint a visible cocoon. The resulting recoil is too small to see. The working picture is a heavy body. Later we will test other pictures that shift efficiency and geometry, and we will look at chemistry that hints at a birthplace in extreme cold. For now, we keep the paradox in front of us. It breathes. It does not budge. The camera moves from equations to images, because the first photographs that showed a forward glow gave the puzzle a face. The first clear portraits arrive like postcards from an older era. Hubble pulls a small shape out of the glare, and it is not the classic comet everyone expects. Instead of a bright core with a tidy tail that streams away from the sun, the object wears a soft teardrop, thickest on the sunward side. The envelope looks like a lantern with its wick toward the light. That single frame poses a simple question. Why would a comet seem brighter where the pressure from sunlight should be pushing material away? Start with what a textbook sketch would show. Radiation pressure and solar wind push fine dust outward, so a normal tail points away from the star. The side toward the sun is usually sharper, then the glow tapers into the long trailing plume. The new image breaks that habit. The head is swollen toward the Sunday. A faint fan still stretches outward into space, but there is a conspicuous brightening in the forward direction. Astronomers call such features anti-tails in some geometries, though in truth the name is a trap, since geometry and grain size can trick the eye. Forward scattering of light by larger grains can pile brightness into the sunward line of sight, even while the grains themselves are not flying into the Sunday. The camera records photons. The photons prefer the forward angle when they bounce off certain particles. The eye reads brightness and tells a misleading story about motion. Time cures. Guesswork. Over weeks, new images arrive from different observatories and with different filters. The forward glow does not vanish with a single change of viewpoint. It waxes and wanes with phase angles, it reshapes as the coma grows, and by late August, a more traditional anti-solar tail begins to lengthen behind the object. The scene evolves, yet the sunward brightening remains a character in the play rather than a cameo. That persistence tells us the effect is not a one-night trick of perspective. It is a real interaction between dust population and sunlight on scales that our models can capture, but that still feel odd to the eye. Morphology matters because it reaches into the mathematics of motion. When astrometrists measure position, they usually do not lock onto a hard nucleus, they lock onto a brightness center. The photocenter can drift if the coma is lopsided. A forward enhancement can pull the centroid a little toward the Sunday. As jets pulse and as dust settles, the centroid can migrate by small fractions of an arc-second. Over many nights, such drifts could mimic or mask tiny dynamical effects. Analysts know this, so they test different apertures, tweak exposure times, and compare visible and infrared views to understand how much the photocenter can lie. The Hubble portrait is not a refutation of the mass inference. It is a caution sign that tells everyone to model the light and the grain physics with respect before writing conclusions in ink. A second thread runs through these pictures. Grain size and composition leave fingerprints on color and on polarized light. Larger grains scatter more forward, which favors a sunward brightening. Dust-rich flows can build a surprisingly compact coma, even as gas extends invisibly far beyond. Infrared instruments that trace gases like carbon dioxide or carbon monoxide can reveal a different shape than visible cameras that respond to dust. That mismatch is not a contradiction. It is a stereoscopic view of different ingredients leaving the same body. In the present case, reports of an extended carbon dioxide coma match the idea that gas is abundant, while the visible cocoon hints at a dust population with sizes and surfaces that love to fling light forward. There is also the question of heat. The side facing the sun will always be the energetic face, so vents that open there can feed a brighter inner coma. If the nucleus rotates slowly enough, that sunward hemisphere can dominate the production for long stretches. If it rotates faster, the dayside and nightside cycle could still favor a forward brightness spike averaged over one spin. These details tie into the same central paradox. More activity tends to mean more recoil. The pictures undeniably speak of activity. The path still looks stubbornly clean. Morphology can move the photocenter, yet the mass inference does not live or die on that single effect. It lives in the joint between spectra, coma size, and the quiet in the residuals. The forward glow therefore becomes a useful test. If chemistry points to volatile ices that wake early, and if infrared maps show a broad gas envelope, and if visible light insists on a sunward brightening driven by grain physics, then the story is coherent. The object is active. The light behaves as expected for large grains. The motion remains surprisingly pure. That coherence does not solve the puzzle, but it strengthens the frame that holds it. The next piece of the frame is the recipe of the vapor itself, because spectra reveal what kind of ice feeds the breath, and that chemistry whispers about where this traveler began. Open the spectrum, and the object stops being a dot. Lines rise where molecules glow. Water announces itself. Carbon dioxide answers from cooler bands. Carbon monoxide joins with a thinner voice. The pattern is not random, it is a fingerprint that tells where the ice was likely born. The surprise sits in a ratio. Carbon dioxide appears unusually strong compared with water for this distance from the Sunday. That is the kind of clue that points away from a warm nursery and toward a cradle in deep cold. Think of a region so far from a parent star that carbon dioxide can freeze beside water ice and stay locked for ages. If such a body is thrown between stars, it will carry that memory the way a pebble carries the feel of the stream that shaped it. Spectroscopy does not work by wish. Photons arrive from the coma and pass through prisms or gratings that spread them by wavelength. Features that match known laboratory lines announce molecules in the gas. Water vapor is the veteran, a common signature in active comets closer in. Carbon monoxide is a tracer of colder chemistry. Carbon dioxide is a powerful coolant and a potent engine for early activity. Seeing all three is not rare. Seeing carbon dioxide so strong this far out is the part that tilts heads. One possibility is that the nucleus formed beyond the carbon dioxide snowline in its home system, where temperatures stay well below 125 degrees below zero on the Celsius scale. In that kind of cold, carbon dioxide becomes solid with ease, then returns to gas at larger heliocentric distances than water would. That would explain why this visitor seemed to wake early, and why the gas envelope in the infrared looks so broad. The picture sharpens when infrared maps show a very extended carbon dioxide coma. Visible images make a compact lantern around the nucleus. Infrared instruments trace a ghostly atmosphere that stretches far beyond the visible glow. That is consistent with a gas that escapes and does not scatter light like dust does. It also matches a scenario in which large grains dominate the visible brightness while gas spreads and thins into space. The chemistry and the morphology speak to each other, and the story they tell is that the object is not pretending to be active. It is active. What does that activity have to do with mass? Chemistry alone does not weigh a comet. It only feeds parameters in the momentum book. If carbon dioxide drives a lot of the flow, then the effective gas speed and the mass loss rate matter for how much recoil should appear. Analysts use line profiles to estimate escape speeds. They compare typical production rates at similar distances for solar system comets. They build a range for how much gas might leave each second. Then they ask how large a non-gravitational acceleration that gas would usually cause. Here is where the mismatch returns. Without flow anywhere near those ranges, a small nucleus should show a measurable drift. The measurements do not demand such a term. The limit on any extra push stays very small. That again leans toward a heavy body that soaks the momentum without obvious motion. A competing view suggests that gas might be escaping in directions that cancel. If vents are spread across the day side, or if shadowed regions leak later as heat lingers, the vector sum of pushes could shrink. Another possibility is that dust masses are high enough that some energy that would go to a net shove instead goes into lofting grains that fall back. Evidence is limited, but one inference is that the persistent forward, brightening hints at a grain population that prefers to scatter rather than to carry long-lived thrust. These options trim the momentum that makes it into a clean orbital signal. They do not vanish it. That is why even conservative modelling still pulls the nucleus toward the heavy end of the scale. The chemistry also carries a cultural weight. Alien ice does not mean alien intent. It means a mix of volatiles that likely formed under different sunlight and different timescales than most of our home comets. A minority view holds that unusual chemistry plus unusual dynamics should make us look for artificial explanations. Responsible practice asks for signatures that are not present. There is no coherent narrowband radio tone. There is no discrete reflective pattern that repeats with a synthetic cadence. The spectrum shows molecules that laboratories on Earth can identify and replicate under natural conditions. It remains uncertain whether the carbon dioxide to water ratio will stay extreme, as the object moves closer to the Sunday water, usually strengthens as distance shrinks. If the ratio changes, that will test models for layering in the nucleus, where different ices wake at different depths and temperatures. If the ratio remains high, that will reinforce the picture of a birthplace beyond familiar snowlines. Either outcome is a clue that tightens the model. Chemistry will not decide mass on its own, yet it narrows the plausible band for momentum inputs. In turn, the motion limits bound mass from below. So we have a traveller whose breath looks colder than ours, whose glow behaves like a field of large grains, and whose movement refuses to confess to a push. That profile only grows stranger when set against the first two visitors we have met from beyond the Sunday. One leaned when it should not have. One behaved exactly like a small comet near home. The third breathes without budging. It is time to place these three on the same chart and see the empty space where this new point sits. Set three portraits on a single table, and the pattern bends in an unexpected way. The first is Oumuamua, a dim sliver that raced through in 2017 with no visible coma, and yet a small non-gravitational acceleration that would not go away. The second is Borisov, a true comet that behaved like the ones we already knew. It shed gas and dust, it curved as expected, it fit the textbook. The third is the present visitor, luminous with a living coma, yet so steady that the fit to pure gravity barely improves when you allow for a push. Three guests from the same grand road between stars, three different introductions to the rules. Begin with Oumuamua because it planted the seed of caution. Observers measured a drift that could not be explained by gravity alone. No gas lines were seen, no broad coma appeared. Theories multiplied. Some suggested hydrogen outgassing that left little trace. Some proposed radiation pressure on a very thin body. The debate still finds new branches, which is a reminder that absence of evidence is not the same as evidence of absence when a target is small and fast. What matters for our chart today is that Oumuamua sits high on acceleration and low on activity, a corner case that keeps the field honest. Borisov steadied the nerves 2 years later. It arrived as a visitor that looked and acted like a comet from our own backyard. Spectra showed water and carbon monoxide. A tail grew as it dove toward the Sunday. The orbit fit improved when analysts added the usual outgassing term. If you draw a rough relationship between mass and non-gravitational acceleration for typical comets, Borisov sits near the line. It became the reassurance that interstellar objects can be normal, and that our tools still work when the guest is familiar. Now place the current traveller on the same plane. Activity is clear. A wide infrared envelope says gas is flowing. The visible cocoon is bright. The forward glow hints at large grains. Yet the measured acceleration remains extremely small. On a mass versus acceleration chart, with Oumuamua out on one flank and Borisov near the central trend, this point falls in an empty region. High activity on the vertical axis, low acceleration on the horizontal axis. It fills a blank space that few would have penciled in before the date of discovery. This empty space matters because it pushes models to cover more ground. If activity can be strong while acceleration is nil, either the object is heavy or the coupling between flow and thrust can be weaker than commonly assumed. The heavy path is tidy. Increase the nucleus radius to a few kilometers, keep density in a cometary range, and the same outflow that would move a small body becomes a tremor beneath detection. The weak, coupling path is messier. You need either counter-directed vents that cancel, or a dust blanket that swallows momentum and hands it back as local turbulence, or some other efficiency loss that cuts the net thrust while preserving the glow. Each of those ideas can work in a slice of parameter space. None yet remove the need for a large mass if the outflow sits near the values implied by the spectra. Reorientation of the through line, we are weighing a breathing traveller by measuring how little it moves. The comparison also clarifies what we mean by mystery. Oumuamua left a hole where the coma should have been. Borisov left a record that reads like a chapter from a familiar book. The current object leaves a line in the ledger of motion that is quieter than its breath would predict. 3 different tensions, 3 different lessons. The field learns in each case to keep the questions simple and the tests sharp. If gas is present, how much momentum does it carry? If thrust is small, how large must the nucleus be? If geometry can fool the eye, How stable is the conclusion when you change the view? There is a human tendency to force a storyline that climbs to a single reveal. Real science more often builds a lattice. The lattice here has rungs across dynamics and chemistry and morphology. Dynamics says acceleration is tiny. Chemistry says carbon dioxide is strong for this distance, which hints at a cold birthplace. Morphology says forward glow is persistent and likely driven by large grains and forward scattering. None of those alone demands a giant. Together, they corral the answer into a smaller yard, where large mass is the straightforward occupant, and where alternatives must show their workings. If this is the third piece on the table, then it also tells us that 3 is not a statistic. 3 is a prologue. Discovery order is not a law. It is a diary of which guests happen to pass close enough for us to see. The next entries will matter more than our interpretations today. Still, we have to act with the pages we have. The pattern so far suggests we should prepare for diversity rather than a single template, and it suggests that our surveys must be tuned for both low-activity bodies that still drift and high-activity bodies that stay still. The paradox in front of us is not only an object, it is the order in which we found it and what that order might be hiding. If giants can arrive early in a small sample, what does that say about the mice we expected to find first? That question opens the door to population, to ejection, and to why our first look at the interstellar zoo might be upside down. The mind expects a parade that begins with small and ends with large. Nature does not owe us that order. If interstellar debris follows the same intuition that rules many collisional systems, there should be far more small fragments than big ones. Small fragments are easier to eject. They require less energy to reach escape speeds. They present larger populations to be sampled by any passing net. By that logic, we should have met a flock of pebbles and boulders before a body that looks like a mountain. Instead, we are staring at something that acts heavy in the first handful of detections. The contradiction is useful. It tells us to interrogate our searchlight, our vantage, and our rules. Start with detection bias. Surveys do not see the sky evenly. They scan where cost and yield make sense. For many asteroid programs, that means long stretches near the ecliptic plane where most native bodies live. If a visitor approaches along that same plane, it enjoys longer visibility in crowd-favored fields and a higher chance of follow-up. If it also carries a bright coma that switches on early, it will cross those fields as a louder target than a dark rock with no vapor. Geometry plus glow can tilt a discovery sequence toward oddities that announce themselves. A faint and fast shard on a steeply inclined path might be missed by the very cadence that finds an object like this one. Add survivorship. The road between stars is not gentle, and it lasts for ages. Small objects have more surface per mass, so radiation and micrometeoroid erosion eat a larger fraction of their bulk. Thermal cycling during random passages near other stars can fatigue them. Some will fracture into dust that surveys cannot see until the grains wake as a brief halo near the sundae. Others will arrive as ghosts too faint for current systems to catch. If many of the mice die or fade during the journey, the early sample at our doorstep could be biased toward the elephants that survive. Now consider how ejection works at the source. Planet-to-planet scattering favors small bodies in simple energy arguments, but real systems are messy. Young clusters cram many stars into tight neighborhoods. Passing stars reach in with large gravitational hands and push on the outer stockpiles. In that environment, rare events become less rare. A heavy body can ride a fortuitous interaction and depart intact. If capture and ejection interactions are common during the first few million years, then the interstellar medium might carry more large seeds than a single star model would predict. We should be careful here. The point is not to proclaim a new rule. The point is to keep our priors flexible until the sample grows. Instrumental timing matters as well. We are entering an era where wide-field cameras and automated pipelines join in a nightly relay that would have stunned astronomers a generation ago. The present object was found by a system designed to catch transients and near-Earth hazards with quick response. This is the same wave that will crest when the Rubin Observatory begins full surveys. The difference between a handful of discoveries and hundreds is not a simple multiplier. It is a change in the kind of statistics we can do. Outliers are loud when there are 3 points. They become context when there are 300. If the size distribution truly rises steeply towards small, Rubin should find that slope. If not, then the early appearance of a heavy traveler is not a fluke, it is a clue. There is also the role of light itself. Dust-rich bodies advertise, gas makes them bigger targets at greater distances. A compact, inactive shard could slip through the same sky unnoticed until it is too close to observe well. That selection effect can make a catalogue look top-heavy. Later, when software is tuned to combine faint short arcs and to flag hyperbolic speeds in the noise, some of those quiet travelers will enter the ledger and pull the distribution back toward the small end. 3 detections cannot define a population. They can still guide strategy. The immediate lesson is to keep multiple nets in the water, fast cadence near the ecliptic for bright comets, extending search latitude to catch high-inclination drifters, algorithmic filters that treat short-arc hyperbolas as worthy of second looks rather than as artifacts, coordinated infrared support to tag gas-rich visitors early. If we can widen the gate, we can learn whether the present giant is a lonely example or a sign that our galaxy moves large stones more often than we thought. Reorientation comes next. We are not only telling a story about size, we are telling a story about how the sky can fool a ruler if the target sits inside a glowing veil. Before we chase where the debris came from, we should make sure we know exactly what we are measuring when we put a crosshair on the light. The next part steps inside the coma and asks how a shifting glow can tug on the point we call the position, and how to keep that tug from writing fictions in the orbit. Imagine a newborn planetary system as a crowded harbour during a storm. Giant planets drift and tug, icy bodies swarm in distant belts. The disk of gas and dust shivers with waves that build and break. From this chaos, a few objects are flung hard enough to clear the shoreline of gravity, sail into the dark between stars. The question is, which machines do the throwing, and what sizes they prefer to hurl? If the heavy traveller before us is not a statistical prank, then somewhere a gun with a long barrel has been at work. Planet-to-planet scattering is the first machine. When young giants migrate, they kick smaller bodies with every near miss. A close pass near a massive planet can boost speed above the escape limit for the host star. This process is common, and it fills local space with exiles. Energy arguments say that lighter projectiles are easier to launch. Small bodies soak up a given push with a larger change in speed. That is why many models expect a sea of fragments with only a thin spray of boulders. Yet nature is messy, and close encounters can stack. A chain of kicks can move a larger body step by step until the last swing clears the hill. Rare does not mean never. The second machine stands outside the system. Young stars often form in clusters. Neighbours pass within a few hundred astronomical units, and their combined gravity leans on outer reservoirs. Think of a wide net of comets that lies beyond the giant planets. A passing star drags one edge of the net and parts of it lift. Many grains fall back, a few stones fall out for good. In such crowded nurseries, large bodies can find the one path that leads to freedom. The cross-section for these events grows with the mass of the intruder and with how long the cluster stays dense. If very young systems eject much of their debris during this era, the seismics in interstellar space may not match the simple picture from a quiet single star case. The third machine is older than planets. Before orbits cool, the disk itself can develop spiral arms and clumps. Gas and dust do not flow like a calm river. They surge. Embedded solids feel drag and gravity that do not cancel. Some will be pumped to the rim and tossed. Some will fall inward and die. If this machine runs early and hard, it can send out ready-made kilometre-scale bodies before planets have time to grind them down. Such disks do not last long. They fade within a few million years. That time window is short but intense. A brief storm can move more mass than a century of drizzle. Each machine has a size signature. Scattering by planets favours the small, but a summary of many rare, strong events can still produce a tail of large bodies. Stellar flybys can move big objects because the lever arm is so long, the potential well of a star is deep, and a wide cloud offers many targets. Disk instabilities can bake clumps into solid seeds that leave as complete cores. If we ever see a demographic that is richer in giants than expected, we will have to weigh these machines against each other and ask which combination matches the curve. None of these guns fire in a clean laboratory. While they eject, they also grind and heat and fracture. Bodies that survive ejection face erosion during the long cruise between stars. That erosion does not care about our taste for tidy categories. It may thin the herd of small wanderers and spare the dense and the large. In that case, the sample we see near the sun is not the sample that left the cradle. It is the sample that lived to tell the tale. The present visitor does not tell us which machine fired it. Chemistry whispers a cold birth, far from a parent star. That could be consistent with outer cloud ejection by a passing star, or with planet scattering that kicks from beyond the snow lines. The dynamical paradox tells us little about the launch. It speaks about how the body moves now, not about how it first shook free. The honest answer is that the machines can all feed the road. Only larger samples will let us read their fingerprints in the sizes of travelers we count. Before we chase those fingerprints too far, we must keep the humility that light demands. The position we fit is not the rock itself. It is a brightness center inside a cloud that moves and changes. If we forget that, we can misread a nudge or miss one entirely. The next part steps into that cloud with a ruler for light. We will see how a photocenter can drift across a living coma, why that matters for tiny accelerations, and how careful observers keep the orbit honest. Stand inside the glow with a ruler in your hand, and the job becomes stranger than it looked from a distance. The nucleus is buried in a soft envelope of dust and gas. Cameras do not see the rock itself. They see a weighted average of brightness across the coma. That average is the photocenter, the point you get when every pixel votes according to how much light it holds. If the coma were perfectly round and steady, the photocenter would sit directly on top of the hidden core. Real comae are not so polite. Jets turn on, grain clouds drift, sunlight sculpts the inner envelope into a lopsided lantern. The measured position can walk a few hundredths of an arc-second toward the brighter side, and that walk can change night to night as geometry shifts. Astrometry cares about this because it hunts for very small deviations from gravity. The residuals that tell you about a tiny non-gravitational push are the same residuals that a shifting photocenter can imitate. A forward brightening can pull the centroid sunward. A jet on the evening limb can tug it sideways. If the coma structure repeats with the rotation of the nucleus, the photocenter dance can appear as a small periodic signal draped on the orbital track. If the structure evolves more slowly, the dance can look like a drift. Either way, pretending that the target is a hard point can build fiction into the fit. The cure is not a single trick. It is a set of habits that respect light. Observers test multiple apertures, which means they measure the position once, using only the inner glow, and again using a wider circle that includes more of the envelope. If the position moves with aperture size, then the coma is telling you that the nucleus does not sit at the brightness center. Analysts then choose an aperture that minimizes bias, or they model the coma to reconstruct the likely offset. Exposure times and filters are adjusted to limit saturation and to reduce the weight of the brightest inner pixels that can drag the centroid toward a jet. Some teams map the inner coma with point spread function fitting, which isolates the sharpest core light from the softer halo. Others combine visible frames with infrared images that trace gas more than dust, then compare centroids across bands to bracket where the rock likely sits. Geometry adds a second layer. The angle between the sun, the object, and Earth changes with time. Forward scattering by larger grains makes the sunward side look brighter when that angle is small. Then the effect fades as the angle grows. If the photocenter follows that brightness lobe, the measured position will creep toward the sun during one part of the approach and relax back later. Careful campaigns plan observations across a range of phase angles and record how the centroid responds. If the response follows the expectations from scattering theory, the offset can be modeled and subtracted. If not, it becomes part of the uncertainty budget, and the mass limits must acknowledge it. Noise has a voice here as well. Sky background, faint field stars, and detector systematics can all push a centroid by tiny amounts. A single observatory can minimize these with repeatable calibration. A network of observatories can beat them down by diversity. What remains after that effort is the real photocenter physics. In the present case, the persistent forward glow in many images means that a sunward offset is plausible. That is not a reason to throw out the astrometric results. It is a reason to fold an offset model into the fit and to watch whether adding a reasonable photocenter correction changes the need for a non-gravitational term. The reported limits already come from analysts who know this playbook. Their residuals incorporate checks for aperture dependence and for phase angle behavior. That is one reason the paradox still holds after months of work. There is a helpful thought experiment that makes the stakes plain. Imagine the nucleus as a black bead hidden inside a milky cloud. A small fan on one side blows the milk gently, and the brightest patch of cloud slides toward the fan. You measure the position of the bright patch, not the bead. If the fan turns on and off with a rhythm, your measurements will wobble in step. If the fan grows stronger as the bead approaches a lamp, your measurements will lean toward the lamp. When you later try to find a tiny extra force in the bead's path, you must first subtract the wobble and the lean that came from the light itself. If you do that subtraction honestly and the path still looks clean, the implication for mass tightens rather than loosens. In practice, teams now pair astrometry with photometry, so that each position has a brightness context. A surge in total light that matches a centroid shift hints at a jet event and earns extra scrutiny. A calm light curve paired with a steady centroid builds confidence that the nightly points are tracing gravity alone. Over months, the collection of such checks makes a case that is stronger than any single night's frame. This is the level of care needed when the signal you seek is as small as a billionth of a meter per second squared. The coma can lie if you let it. It also tells the truth if you listen properly. The payoff is clarity about what the paradox is and what it is not. The paradox is not a naive reading of pretty pictures. It is a statement that survives coma modeling, aperture tests, and phase angle sweeps. The object breathes and leaves a visible cloak. The cloak can tug the centroid, and the teams account for that. After the accounting, the orbit still sits very close to gravity. That is why the lower limit on mass feels sturdy, even as details continue to create, sharpen. With that confidence set, we can step back from the cloud and look at the planet-sized effort that made this subtle dance readable at all. The world watched as one telescope, and the quiet in the combined record is what turns breath without shove into a scientific claim. Begin with sunrise sweeping a blue line across the Pacific. Domes in Hawaii close as dawn reaches them. Domes in Chile open into twilight. Europe prepares under a cooling sky. Australia waits for the Southern Cross to lift. The planet turns, and at every step a different mirror takes the baton. The visitor moves a fraction against the fixed web of stars. The handoff repeats. Night after night, a chain of images gathers, each one a syllable in a very slow sentence. This is what it means for the world to act as a single instrument. No one sight can hold a target for months. The planet can. Inside each dome, the craft looks simple when told plainly. You center the field so that the visitor and a litter of catalogued stars share the same frame. You expose just long enough that the point source rises above noise while the stars stay within their linear counts. You record time with a clock that has been disciplined to a standard that will not drift. You correct distortions that matter at the margin. You register the frame to a celestial coordinate grid whose stars have been measured by space missions with accuracies that were unthinkable one generation ago. Right ascension, declination, uncertainty ellipses. Then you send your points into the river of points that everyone else is building. The value of that river grows as it lengthens. A single night can be fooled by weather or by a slight focus error. A week can be fooled by a lull in activity that does not return. A month begins to feel like truth. Over 4 months of coverage, the residuals between measured positions and a pure gravity fit, shrink, and settle. They do not want an extra term. They do not want the addition of a small push that depends on distance from the Sunday. Analysts will try one anyway. They will add a parameter that stands in for outgassing thrust and see whether the scatter tightens. If it does not, that parameter becomes an upper limit. When the limit sits in the realm of billionths of a meter per second squared, it tells you that any extra push is faint indeed. The numbers only matter because the habits are sound. Teams cross-check instruments by observing the same field on the same night from different latitudes. They swap filters to see if chromatic effects move the centroid. They compare short and long exposures to understand how blooming shifts the weight of inner pixels. They reject frames when the seeing drifts beyond a threshold. They keep a ledger of calibration stars that flags any night when the plate solution shows a hidden flex in the mount or a thin layer of haze. This is not drudgery. It is the way precision becomes possible with tools that are not perfect. Another strength of a world instrument is its diversity of eyes. Large telescopes can reach faint signals and pull structure out of the inner coma. Small robotic arrays can trace motion with relentless cadence. Amateurs who have mastered flat fields and bias frames can fill gaps and catch flares that would otherwise slip by. When points from such different sources line up on the same curve, with uncertainties that overlap in a sensible way, the faith in the curve grows. If the curve does not bend, the absence is meaningful. Photometry runs alongside the position work. Light curves note when the visitor brightens and by how much. If a spike in brightness is paired with a measurable centroid shift, that night earns extra caution. If the brightness changes slowly without jitters, and the centroid remains steady within the noise, the astrometric points from that night earn more trust. Over a long baseline, this pairing of position and brightness builds a multi-dimensional record that resists simple mistakes. The story is not only about patient accumulation, it is also about choreography. Coordinators schedule windows so that the target never sleeps. They plan observations at a spread of phase angles to sample how forward scattering changes the inner glow. They set up interleaved sequences with infrared instruments that sniff gas, so that the visible centroid has a context in which to live. The result is not one perfect night. It is a chorus that can sing a quiet note for a very long time. What comes out of this world-sized effort is a claim that is modest and strong. The orbit of the visitor is well fit by gravity alone over the observed arc. The limit on any extra acceleration is very small. The coma is real. The gas is real. The two ideas, real coma and tiny push, meet and make a lower bound on mass that is high for an interstellar traveler. This is enough to guide the next choices. It tells mission planners when a distant look will still matter. It tells spectroscopists when to expect changes as different ices wake. It tells modelers which efficiency terms must be pressed hardest. The planet has done its work from its surface. The next vantage point does not turn on our rotation. It rides a red world that will happen to be nearby. As Earth moves into a season of glare, Mars will watch from a different angle. Its orbiters can turn cameras outward and see the glow without our atmospheric blur. That window opens in early October. The stage is set to see whether the silence in the residuals survives a second geometry, and whether the forward glow plays the same trick when seen from another world. Picture Mars as a quiet balcony above a busy square. Earth sits in bright glare near the Sunday. The visitor slides through that glare from our perspective. From Mars, the geometry is kinder. The object will pass at a respectful distance measured in tens of millions of kilometers, far enough to stay safe, close enough that sensitive cameras can take its measure. The question is simple. What can Mars-born eyes see that Earth cannot see during this window? And will those views confirm the strange balance of breadth and steadiness that has defined the story so far? Start with the instruments that might try. Mars Express carries cameras and spectrometers that have stared at the planet for years. The Trace Gas Orbiter can look outward when plans allow. MAVEN studies the air of Mars, yet its sensors can contribute when pointed with care. None of these spacecraft were designed to chase interstellar visitors. They were built to read a planet. That is a limitation but also a virtue. Their optics are stable. Their clocks are good. Their teams know exactly how to squeeze signal from faint targets. With careful planning, they can take repeated images through different filters and build a light curve from a vantage that is off to one side of the Earth's sunline. The object remains a point for them. It will not resolve into a nucleus and a veil, but points are enough when you seek subtle truths. A point that brightens and dims will tell you about activity. A point that sits with a different phase angle will tell you how forward scattering shapes the glow. This is the heart of the Mars advantage. Phase angle is the angle sun to object to observer. From Earth, that angle shrinks as the visitor approaches the region near the Sunday. From Mars, it can stay larger for a time, which reduces the forward scattering spike that has been brightening the sunward side in our images. If a series of Mars vantage measurements show a fainter forward lobe, that supports the idea that large grains have been doing the heavy lifting in visible light. If the lobe stays strong, even at less favorable angles, that hints at dust physics that lean farther from the norm. Either result reduces ambiguity in the coma models that feed the orbit fits. Mars can also supply cadence during a difficult stretch. As the visitor sinks into the daylight glare for Earth-based telescopes, Mars orbiters can schedule sequences that cover the same days and weeks. That continuity keeps the light curve from tearing. A smooth record lets analysts test whether the object is pulsing or steady. If a pulse is found that repeats with a period, it could be the voice of a rotation cycle. Rotation couples to jets, jets couple to recoil. A rotation-linked rhythm would let modelers test how much of the expected thrust would cancel over a spin, and whether such cancellation could plausibly hide inside the small limits set by Earth astrometry. There are practical limits that must be named. Distances of tens of millions of kilometers turn a powerful camera into a precise photometer. Mars Reconnaissance Orbiter carries a famous high-resolution imager, but its sharpest vision is meant for the ground under its path. Against a black sky, its strength is pointing and stability, not a resolved shape at such long range. That is acceptable. The science need here is not a portrait of the nucleus. It is a set of brightness readings in known filters taken at known angles across known dates. Those simple ingredients are the ones that feed the chemistry and dust models that must be consistent with the Earth-based spectra. Safety requires no drama. 30 million kilometers is far. There is no risk to spacecraft or to Mars. The only risk is schedule, power, and competition with primary mission goals. If even a few sessions are approved, there will be enough to lock a small set of constraints into place. A set of photometry points, a measure of color as a function of phase, a check on whether any sudden surge in brightness appears during the period when Earth is mostly blind. Reorientation of the through line. We keep weighing a breathing traveler by checking whether new angles change old balances. There is also a cultural dividend that is easy to overlook. A measurement from another world turns the solar system into an instrument with depth. Two observers in different places can triangulate, not position in this case, but behavior. Mars confirms whether the forward glow belongs to geometry as much as to dust. Mars checks whether activity rises in a smooth arc or in ragged bursts. Mars can even test whether the object flickers on a timescale that would show a spin. These are not luxuries. They are tests that decide which knobs to turn hardest in the momentum model that links activity to thrust. If the Mars window delivers quiet data that fit the cleaner picture, the paradox of breath without shove becomes stronger. If it delivers a surprise, perhaps a sudden flare or a color change, the model will change in step. Either outcome improves the map we carry into the next opportunity. That opportunity sits deeper in the solar system, where a giant planet waits. There, a veteran spacecraft circles in magnetic night and day. There, attempting alignment in March offers either an audacious chase or a patient watch from afar. The balcony view gives way to a coliseum. The stakes rise. The rules of fuel and lifetime enter the script. There is a place where telescopes on Earth fall silent, not because interest fades, but because the sky turns into a white sea. The visitor folds itself into that sea as it rounds the far side of the Sunday. To an observer on our planet, the target becomes a spark drowned by the day. Yet the solar system contains scouts that work close to the fire. They watch in light that bruises instruments, and in a haze that would blind a ground-based mirror. If we want to know what the coma does when the heat is highest, we must lean on these scouts and on a geometry that ignores the limitations of our horizon. Think first about vantage. When the visitor nears perihelion, the line from Earth to the object runs almost through the Sunday air, scatters light. Optics scatter light. At some angle, the scattered brightness climbs faster than the object brightens. The result is practical invisibility. A spacecraft that orbits within the inner heliosphere does not, to share our handicap. It can look away from the disk and still place the visitor against a sky that is bright but not blinding. The Parker Solar Probe carries cameras that live for this kind of work. They image faint dust and solar wind structures near the corona. In those cameras, the visitor could appear as a compact fan or as a soft knob on a river of scattered light. A handful of frames at the right time could tell us whether activity surges as the heat peaks, or whether the constant breathing we have seen simply continues at a higher hum. Glare is not the only enemy. The closer the object gets to the sun, the more violent the environment becomes. Radiation pressure grows, the solar wind stiffens. Dust grains that were quiet at 3 astronomical units begin to move in more complicated paths. Large grains may still fly almost ballistically, which keeps the forward glow honest. Fine grains begin to dance to the tune of light and magnetism. In this regime, a spacecraft image series can test ideas that were only sketches during the earlier approach. Does the forward brightening sharpen because forward scattering grows with phase angle? Or does the glow soften because grain size distributions change as fragile particles fracture? If the sun-side view records a change in the shape of the inner coma that matches one model more than another, the photometric corrections that feed the orbit solution will gain a firmer footing. Perihelion also tests chemistry. Carbon dioxide can drive activity at larger distances. Water becomes more important closer in. A sequence of near-solar images cannot pass individual spectral lines, but it can act as a crude calorimeter. If brightness climbs in a smooth arc that follows the expected rise of water-driven sublimation, then the ratio of gas species is behaving as simple models predict. If brightness jumps in lurches or stalls when simple heating curves say it should rise, then layering and vents and shadowed pockets are dominating. The flow. Those behaviors speak to how momentum is delivered to the nucleus. Recoil that cancels in one rotation might still produce a net drift if vent patterns evolve with temperature. A sun-side light curve can catch that evolution in the act. The most valuable product of the inner watchers may be continuity. Earth sees an object that fades into glare, then later reappears. Data taken near the sun softens that gap into a continuous narrative. A clean record matters because the paradox hangs on long averages. A single burst can move a nucleus more than a week of quiet flow. If a burst happens during the blackout, an orbit fit that ignores it could set a mass floor that is too firm. A handful of images or brightness points from the blackout window give analysts a way to look for such bursts. Even a negative result is worth gold. No burst seen as a constraint that allows the earlier months of quiet to stand as a fair summary of behavior. There is prudence in this plan. Inner heliosphere cameras are not built to weigh comets. They are built to watch the Sunday noise patterns are different. Calibrations are tuned to coronal structures and to dust trails. Pointing constraints and data rates are not governed by a campaign to follow a faint visitor. A few slices of time may be all that can be spared. That is enough. This script does not need a movie. It needs a handful of stills that lock the behavior during the weeks when Earth looks away. What can go wrong? Brightness could be too low for a clear detection. The object could pass through a background feature in the solar wind that complicates separation. A micrometeor shower could dust a lens and lower contrast. These are reasonable risks. They do not erase the value of trying. The reward is a test that plays directly into the mystery. If the coma swells and the forward glow keeps its character, then the story of large grains and efficient forward scattering gains weight. If the coma flickers in a way that suggests rotating vents and varying efficiency, then the case for partial momentum cancellation strengthens. In either scenario, the lower bound on mass is clarified, since a model that links breathing to shove can be tuned with the right shape of light. This part of the journey is the hardest to watch, and the most important for the physics of activity. The visitor passes nearest to the furnace, then swings outward along a track we can see again. After the glare, the path leads toward a region ruled by a planet with a deep well of gravity and a patient sentinel in orbit. The next chance does not fight daylight. It tests courage and fuel. It asks whether a mission whose work is nearly done can throw itself onto a new path to chase a story that began with a whisper and a quiet line on a plot. There are moments when the solar system lays out a chessboard and dares you to make a bold move. March of 2026 is one of those moments. The visitor will pass within a fraction of an astronomical unit of Jupiter, close by the measure of a giant planet and wide by the measure of a spacecraft camera. In that neighborhood, an aging explorer circles under auroras and radio storms. Juno has mapped gravity fields and magnetic curtains. It has tasted lightning light and watched cyclones spin like pearl strings. Now a new temptation appears. Could those engines fire one last careful time and curve a path toward a meeting with a traveler from between the stars? The proposal is simple in outline and hard in practice. A burn near Perigove gives the best change in speed for the fuel you spend. The deeper the spacecraft is in Jupiter's well, the more each second of engine time buys. Engineers have a word for this leverage. Pilots feel it as a slingshot. A small adjustment at the right moment can shift a future position by millions of kilometers. The question is not whether the math works. It does. The question is whether the remaining fuel, the health of the valves and lines, and the window of time available are enough to reach a useful flyby distance, then to point the instruments and hold the link home long enough to return data. What would such a chase buy? Dust composition in situ, rather than inferred from light. Grain-size distributions measured by how particles strike a detector, rather than by how they scatter. Magnetic and plasma signatures of gas flow around a moving nucleus. Even a distant past that does not resolve the nucleus could see changes in charged particle densities and could measure how sunlight ionizes the coma at Jupiter's distance. A closer past could sniff isotopes in released water and carbon-bearing molecules. Those measurements would turn a story told in careful inferences into a story told with samples of the environment itself. The value is obvious to anyone who has chased comets with a camera and wished for a scoop. The cost is also obvious. Juno carries a finite load of propellant. It was not designed to wander far from a family of looping orbits that trade altitude for time inside the radiation belts. Every pulse of the engine is a bet placed against the future. A redirection toward a rendezvous would likely consume most of what is left, ending the possibility of continued Jovian mapping. There is also risk in the unknown. A valve could stick open. A line could run colder or hotter than models expect. A burn could fall short of plan and waste the chance without delivering the prize. Mission managers carry these worries like weights. Their job is to make science that survives its own ambition. There are intermediate options on the table. Juno could remain in its current campaign and adjust only pointing during the window when the visitor is nearest. Instruments could be tuned for distant observations, not a flyby, gathering radio and plasma context, and a faint light curve from a high-latitude view. Other spacecraft could be enlisted to add distant eyes. A chorus rather than a solo. These paths buy safety and still deliver value. They do not deliver the thrill of a near pass. The choice is a portfolio problem. How much certain knowledge do you trade for a low probability of a spectacular return? A responsible plan begins with evidence checklists. What signatures would change minds about the mass puzzle or about momentum efficiency? A clean measurement of dust-to-gas ratio in situ would anchor the coupling term that has absorbed so much argument. A spectrum of neutral and ionized species near the body would tell you what drives activity at long range. A time series of fields and particles would show how the coma breathes under sunlight at Jupiter's distance. These are not ornaments. They are the exact pieces that fit the holes in the present model. There is a public dimension that cannot be ignored. When a spacecraft built for one world is asked to chase a new question, citizens who funded the first mission deserve to hear the case in plain speech. The case here is strong but not romantic. Either we accept a small chance at a first close look at interstellar material, or we continue to finish a program that has already transformed our view of a giant planet. There is no villain in either path. There is only judgment about timing, about rarity, and about the shape of opportunity. Reorientation of the through line, we are still weighing a breathing traveler, now by asking whether a chase can turn inference into contact. In the end, the alignment in March is a temptation, not a mandate. The science community can prepare either way. If a chase goes forward, theory teams can sharpen predictions about dust flux and gas composition. If it does not, ground and space observatories can schedule coordinated campaigns to catch the same window from afar. Both paths need rules of evidence, and both will be judged by how well they turn spectacular images into hard claims. The next part lays down that rubric. What would count as proof, and what would count as a clean falsifier, in the story where breath without shove has become the central riddle. This story thrives on wonder, but it must be steered by rules. If a traveler breathes and does not budge, what observations would move the needle from intriguing to decisive? Proof in planetary science is not a trumpet blast. It is a short list of signatures that are specific, measurable, and hard for nature to fake. The first category is motion. The second is light. The third is particles and fields. The fourth is time, because repetition reveals intent while noise rarely repeats itself in the same way. Begin with motion, since the paradox lives there. A clean detection of acceleration that cannot be explained by sunlight, gas recoil, or geometry would be a turning point. Analysts already fit orbits with a term that stands for outgassing thrust. A stronger claim would be a change that appears suddenly, and then persists with a profile that matches no plausible vent pattern. An example would be a velocity increment that starts when the body is far from perihelion and continues through a stretch where activity, as measured by spectra and photometry, remains flat. Another example would be a kink in the track that repeats with a period that does not match any rotation seen in the light curve. Either would demand a force that does not ride on warm ice. Light carries a second set of tests. A narrow radio signal that stays coherent and tracks the visitor across the sky is one. Nature produces many radio tones, but most are broad or drift with plasma conditions. A persistent tone with narrow width and controllable drift would be hard to explain without technology. Optical reflectance is another test. A surface that shows a bidirectional reflectance pattern with features that repeat at fixed angles, independent of phase hints at engineered texture. Thermal light offers a third test. A temperature map that remains uniform across day and night at a level incompatible with rotation and insulation suggests ongoing energy management. These light-based signatures are not expected. They are standards to be checked so that rumor does not outrun measurement. Particles and fields speak in the language of nearby space. If a spacecraft can sample dust near the coma, the size and speed distribution of grains becomes a direct measure of how momentum leaves the nucleus. A heavy tail of large grains would support the forward scattering story and the idea that much of the visible glow produces little thrust. A sensor that counts ions and electrons can trace how gas becomes plasma as sunlight strips electrons from escaping molecules. Ratios of neutral to ionized species help test whether activity tracks heat or some other driver. A magnetometer can look for coherent field structures that stick to the body in ways that simple sublimation would not produce. None of these alone decides the question of mass. Together, they fix the coupling term that has carried so much uncertainty in the momentum balance. Time is the referee for every other test. A single frame can be a trick. A series across weeks is harder to fool. If motion changes correlate with known heating cycles and phase angle, that is natural. If changes fight those cycles, caution rises. If a purported radio line vanishes when independent groups try to see it, the claim fades. If it reappears at predicted times for predicted durations, interest grows. A testable prediction that survives is the gold standard. It is also the best protection against stories that thrive on novelty but wilt in daylight. There is a mirror list of falsifiers that would soften the mystery without erasing it. A robust rotation period tied to light curve modulations that match gentle jetting would make momentum cancellation more plausible. An infrared spectrum that shows water rising sharply closer to the sun and a matching rise in coma brightness would favor standard sublimation physics. A coordinated set of astrometric points before and after perihelion that still refuse a non-gravitational term would raise the mass floor with fewer caveats about coma geometry. These are not defeats for drama, they are victories for clarity. It remains uncertain whether the forward glow will keep its strength across the full range of phase angles available this season. That uncertainty is useful. If it fades as expected, photometric corrections shrink and the orbit fit gains confidence. If it persists, dust models must change in a way that can be tested, perhaps through polarization measurements that sort grain sizes by how they twist light. In either case, the rule holds. Evidence first, story after. A final note belongs to process. Preprints are a workshop floor, not a courtroom. Peer review is a pressure test. Independent reduction of the same data by groups that do not share tools or priors is the crucible for claims this delicate. When a result survives that gauntlet, it becomes the kind of proof that can support a scaffold of new models. Until then, we treat extraordinary interpretations as guests that must show their invitation at the door and their passport at the table. With the rubric on the wall, we can return to a specific riddle inside the spectra. Nickel sings, iron stays quiet. That is chemistry with a sharp edge, because natural mechanisms can prefer one metal over another when light and cold work together in peculiar ways. The next chapter opens that file and asks how atoms are freed from grains in the dark and why this visitor may hum in nickel while iron declines to join. Open the spectrum in the red and near-infrared, and a peculiar music begins. Several bright notes of nickel rise cleanly between 700 and 900 nanometers. Where iron would usually answer with its own set of lines, the plot stays quiet or speaks only in whispers near the noise floor. The result is not a rumour, tucked in a wing of the data. It is a pattern seen over multiple nights as activity increased. Nickel keeps singing, iron refuses a solo. Why would a cometary coma prefer one metal when both are common in meteoritic grains, and often travel together in natural alloys and sulfides? Begin with what atoms must overcome to appear as light. Metals in comet dust are usually locked inside minerals. Heat alone at these distances is rarely enough to vaporize those minerals. Another path is needed. One possibility is photon-driven release from grain surfaces. Ultraviolet photons can break bonds and free atoms that sit in the outermost layers of a mineral, especially in cold environments where thermal motion does not shake them loose first. If nickel occupies sites in the grain that are more exposed or are bound in configurations that absorb photons efficiently, it could be liberated more readily than iron. Evidence is limited, but one inference is that the steep rise of nickel line strength with decreasing distance to the Sun hints at a threshold process that accelerates once irradiance crosses a critical level. A competing view suggests that metal-bearing organics or carbonyl-style complexes form under deep cold and then decompose under sunlight, releasing nickel more readily than iron. Laboratory chemistry shows that some nickel compounds are more volatile or more easily dissociated than their iron cousins. It remains uncertain whether such complexes can form and persist in the interiors of icy bodies over millions of years. If they can, a gentle increase in sunlight could crack them open and lift nickel into the coma while iron stays mostly caged. Another natural filter lives in the grains themselves. Grain size controls temperature spikes from single photon hits and from exothermic surface reactions. Very small grains can heat locally for brief moments. If nickel-bearing microinclusions reach release temperatures during these spikes and iron-bearing inclusions do not, the coma would see more nickel atoms for the same overall dust mass. A minority view holds that micrometeoroid impacts inside the coma can sputter atoms from grain surfaces with a bias set by mineral hardness and bond energies. In that case, nickel could again be favored without calling on exotic chemistry. Spectroscopy gives more than a list of lines. Line widths carry thermal and bulk motion information. Broader lines can mean higher kinetic temperatures or faster flows away from the nucleus. Line ratios respond to excitation conditions in the gas. If the nickel lines change shape and relative strength in ways that track solar distance and production rates of water and carbon dioxide, we gain clues about where and how release happens. A narrowing, as the object recedes, would favor a near-nuclear source that cools as activity declines. A persistent width with a changing centroid would hint at distributed release from grains that drift far from the body before yielding their atoms. Spatial information would be decisive. A map of nickel emission that peaks close to the nucleus would support direct surface processes. A wide halo of nickel that brightens far from the core would point to delayed release from dust as it travels. Instruments that can slice the coma into narrow fields will be crucial here. So will observations taken at different phase angles, since forward scattering by dust can distort apparent structures and confuse the location of true sources. It is important to note what the nickel puzzle does not imply. Nickel lines are not a signature of technology. They are a signature of atoms in a low-density gas being excited and emitting at known wavelengths. Natural mechanisms can prefer nickel over iron under specific temperature and photon conditions. If an engineered alloy were somehow present, spectra would still show atoms, not brand names. Sensational conclusions would require other evidence entirely, such as coherent radio signals, engineered reflectance, or non-ballistic motions that do not match sublimation physics. None of those are present. The path forward runs through tests that can be planned now. Watch how nickel responds as water strengthens closer to the sunday. If nickel rises in lockstep with water, then thermal release from heated grains may dominate. If nickel peaks earlier and then flattens as water climbs, photon-driven pathways that are efficient at lower temperatures become more likely. Compare nickel strengths with independent measures of dust to gas ratio. A dust-rich coma should produce more surface area for photodesorption. Look for polarization changes that mark shifts in grain sizes, since those shifts affect local heating and release. Ask whether any weak iron features finally emerge near perihelion. Even an upper limit that tightens would constrain which mineral hosts are plausible. Nickel without iron is not a verdict. It is a riddle that binds chemistry to the same larger story we have been telling, a story of dust that bends light in forward directions and of gas that breathes without pushing much at all. The grains that free nickel may also be the grains that build the sunward glow. To test that connection, we turn from atoms to particles, from spectral lines to the way light scatters around a moving cloud. That path leads straight to a glow that seems to point the wrong way and to the grain physics that can make the wrong way right. Stand at the correct angle, and a fog can look like a mirror. The same trick happens in space. When sunlight hits grains that are larger than the wavelength of light, the scattered glow piles up in the forward direction. Point your camera from nearly behind the sun, and the coma brightens where your instincts predict a shadow. That is the seed of the sunward glow. It is not dust flying into the star. It is light choosing to travel toward you after it strikes certain grains. The visitor wears this effect like a badge, and the badge keeps shining across changes in geometry long enough to make careful minds pay attention. Begin with grain size, because size sets the game. Very fine dust scatters almost symmetrically. Larger grains behave like tiny lenses that bend light forward. The effect grows stronger as the phase angle shrinks. That angle is the gap between the lines from object to sun and from object to observer. Near zero, the forward spike can become intense. The shape of that spike depends on size, on surface roughness, and on the refractive index of whatever the grain is made of. Ices and organics differ. Silicates behave in their own way. When observers saw a brightening toward the sun that refused to vanish with a modest change in angle, the simplest reading was a population rich in large grains that favor forward scattering under many conditions. Grain dynamics are the second half of the picture. Gas pulls small grains outward, and radiation pressure pushes them away from the sunday. Large grains are heavier, and their area to mass ratio is lower, so sunlight shoves them less. They leave the nucleus on slow arcs that can be almost ballistic. If you imagine a spray of pebbles leaving a fountain and then falling in a graceful sheet, you get the idea. The sheet can look brighter toward the sun from the right vantage, because the forward scatter is strongest there. Over days, the sheet slides and thickens. The brightness center can drift sunward, while the tail in the classical sense still grows on the antisolar side. This is why a single image can be a liar unless you understand both the light and the motion of the dust. There is a third ingredient, the color of the glow. Forward scattering often comes with a gentle reddening if the grains are coated with complex organics. Polarization adds another handle. Light that bounces off surfaces twists in ways that depend on size and texture. A sequence of polarimetric measurements across phase angle can separate populations. If the sunward lobe shows a distinctive polarization curve, analysts can infer not only size, but also whether the surface is fluffy or compact. Fluffy, grains break easily and can feed gas production through fresh area. Compact grains last longer and carry momentum farther before they fall behind. These properties matter because the link between visible brightness and mechanical shove runs through the grains that carry both. Now return to the paradox and ask what the glow can tell us about momentum. If large grains dominate the visible light, then a bright coma does not guarantee a strong push. Large grains can lift out with help from gas, then fall back or drift in arcs that do not add much to a net thrust. Gas momentum still exists, but some of it goes into a cloud that does little to move the nucleus over long arcs. In that case, the object can look vivid and still fail to show the nudge that classic comets reveal. This does not prove a giant on its own. It narrows the efficiency term that sits between activity and recoil, the same term that modelers tune when they ask how much push should appear in the orbit. There is a practical test that draws all of this together. Watch the forward glow through a season of changing phase angles. If its strength tracks the well-known phase function for large grains, then the correction to the photocenter is predictable and can be removed from the astrometry with confidence. If it refuses to follow that law, then either the size distribution is changing quickly, or the geometry includes jets that alter the inner coma in a way that is not captured by a simple scattering model. In either case, photometry and polarization become the tools that keep the orbit honest. A final note belongs to timescales. Grains do not live forever in the coma. They fragment, they sublimate. They collide. If forward scattering remains strong across weeks, large grains must be replenished. That implies steady activity from sunward regions, or a rotation that keeps feeding the same sector. Such persistence explains why the glow stayed in the script across months. It also makes clear why the motion still looks pure. The same fountain that maintains the glow can lock its momentum into a dust sheet that rarely adds up to a steady shove. We are circling the same conclusion from different sides. Light tells us that the coma is real, and that large grains dance near the line to the Sunday dynamics tells us that the push on the nucleus is small despite that glow. Chemistry tells us that cold-born ices wake early and feed wide gas envelopes. All three threads point back to the balance of momentum. To make that balance explicit, we step into the engine room where numbers rule, where gas speeds and mass loss become sliders, and where the heavy answer survives even after every knob is turned. Open the ledger and write the first line. Momentum out equals momentum in. Gas leaves, the nucleus reacts. This is the quiet arithmetic that hides behind every dramatic image. We can dress it in symbols if we like, but a clean picture works just as well. Imagine a scale. On one plate sits the stream of molecules that depart each second. On the other plate sits the nucleus. The stream pulls in one direction, the body slides in the other. When astronomers say the slide is almost invisible, they are telling you that the stream must be light, or the body must be heavy, or the way momentum couples between them must be inefficient. Start with values that are friendly to the imagination. Gas speeds in active comets often sit in the few hundred meters per second range. That is fast enough to cross a football field before you count to 1. Production rates for a modestly active coma can live near hundreds of kilograms per second. That is roughly the mass of 2 people, leaving every tick of the clock. Multiply the mass flow by the speed and you get a momentum rate. That rate is the push the jets could deliver if all of it acted in the same direction. Comets usually do not give you that simple case. Vents fire from different spots. The rotation of the nucleus turns jets into arcs that partly forward, cancel. Dust can soak energy before falling back. These realities are why modelers insert an efficiency, the fraction of escaping momentum that turns into a net thrust on the core. Now slide the knobs and see what breaks. Lower the production rate by a factor of 2. The push drops by the same factor. Halve the gas speed by changing assumptions about temperature or line broadening. The push drops again. Reduce the efficiency because vents face in different directions or because dust steals momentum. The push drops once more. After all of those concessions, the calculation still lands in a range where a small nucleus should show a measurable acceleration over months. Yet the orbit fit does not ask for such a term. Push the concessions farther, and you begin to contradict things that the images and spectra already told us. The coma is wide, the lines are real, the activity persists. The ledger refuses to balance unless the body on the other plate weighs a great deal. There are refined versions of this exercise that try to capture more of the texture. Analysts choose gas speeds from line profiles rather than from memory. They allow production rates to vary with heliocentric distance according to curves that match water and carbon dioxide. They let vents switch on and off with rotation so that net thrust alternates direction every few hours. Then they integrate the push over weeks to see what remains after the seesaw. These models dampen the effective acceleration. They rarely erase it entirely. The integration acts like a smoothing filter. Bursts become blips. A persistent bias in where vents live on the surface will still leave a net tug over long arcs. If that tug fails to appear at the level instruments can see, mass rises in the solution like a tide. A different path tries to hide momentum without demanding a giant. It assumes that gas mostly leaves through porous drifts of dust. Momentum gets shuffled into eddies and lost as heat before it can push the nucleus. The coma still brightens, the outflow still feeds lines in spectra. The mechanical response is quiet. This idea is not fantasy. Natural surfaces can behave like filters that waste energy in small-scale turbulence. The question is, how much loss is plausible? If you take the loss too far, you must also explain how a thick veil of dust produces such a clean look in the infrared gas maps. You must explain how the forward glow stays sharp if grains spend long in chaotic recirculation near the vents. The more you add to the loss column, the more the pictures begin to disagree. There is comfort in the limits because they are falsifiable. If later spectra revise the production rates downward by large factors, the mass floor will relax. If gas speeds are lower than early estimates, the same happens. If polarization and phase curves prove that the dust layer traps momentum with unusual efficiency, models will accept more hiding. Each of these is a real test that teams can run with new data. Until the tests land, a heavy nucleus remains the clean way to reconcile breathing with stillness. A single warning belongs in the ledger. Comets have moods. A quiet month can hide a short violent hour. A sudden outburst could dump momentum into one direction and then sleep. If that hour happens inside a gap in observations, a clean orbit fit might miss the nudge. That is why the plan to watch near the Sun and from Mars matters so much. Those windows reduce the chance that a brief shove breaks the balance without being recorded. If no such bursts appear, confidence in the long average grows. Reorientation of the through line, we are still weighing a breathing traveller by asking how much shove survives even after every allowance is made for loss and noise. The next question is human. People hear the word massive and feel unease. They imagine a threat. This is the part where science must be plain. The geometry of the orbit does not aim at us. The distances remain large. Curiosity drives. The chase, not alarm. Before the story turns back to media storms and cultural mirrors, we pause to make that safety case clearly and briefly. Begin with a picture that calms the pulse. Draw the Sun at the center. Place Earth on a ring at 1 astronomical unit. Mark the visitor's path as a long hyperbolic curve that clips the inner system without pointing at us. The line comes near by human standards and far by planetary standards. The closest approach to Earth is about 1.8 astronomical units in late December. That is roughly 170 million miles. For scale, the Moon is 250,000 miles away. The visitor will be hundreds of times farther than the Moon at its nearest. In plain language, we are spectators, not targets. Safety is not a feeling, it is geometry plus time. The orbit solution that hundreds of observatories refined shows a track that never crosses the narrow lane where Earth will be. The uncertainties are small, because the arc has been watched for months and will be watched for many more. Even if tiny non-gravitational effects were larger than current limits, the change in position over the coming seasons would be tiny compared with the distance that separates the object from our planet. This is why teams can focus on chemistry and dust without pausing to write hazard bulletins. Curiosity is the engine here. People also worry about surprises. Could a sudden outburst change the path? Outgassing can change speed by small amounts. The resulting position shift builds slowly and can be tracked with continued measurements. A violent breakup could spread fragments along the same path like pearls on a string. That looks dramatic in a photograph and dull in an orbit plot. The center of mass still follows nearly the same curve. None of these scenarios turns a safe pass into a threat. They do change how pretty the coma will look and how bright the dust sheet may become. There is a different kind of safety that matters to scientists. Instruments and schedules live in budgets. Observing time is scarce. During the weeks when glare blinds Earth-based telescopes, it is tempting to imagine that something important will happen in the dark. That is why missions near the Sun and orbiters at Mars plan to watch. If those windows return quiet records, then the long average behavior is confirmed. If they find a burst, it will be measured and added to the ledger. Either way, uncertainty shrinks. Safety in the scientific sense means fewer blind spots, not louder alarms. Another common fear appears whenever a large mass is mentioned. People hear giant and think of impacts. Here the lesson of scale is simple. The solar system is vast, even near misses are enormous by human standards. A visitor passing at 1.8 astronomical units is not a near miss. It is a distant wave from across the park. The track through the solar system is also steep. Hyperbolic visitors are not captured into short-period loops that return often. They come, they sweep through, they leave for deep space. The timescales of risk for Earth come from different families of objects, the ones that live near our orbit and cross it on a schedule. Those are tracked by dedicated surveys that run every clear night. This traveller is not one of them. There is value in saying what we do not do. We do not ignore small risks. If a path ever carried a real chance of intersection with Earth or Mars or a major satellite, Agencies would coordinate campaigns that compute windows with finer meshes and that plan contingencies for observation. That practice exists, and it works. It is not needed here. The story of this object is not planetary defense. It is planetary curiosity sharpened by a paradox. It breathes and does not budge. That is a reason to point instruments, not a reason to rehearse evacuation plans. Reorientation of the through line. We continue to weigh a breathing traveler, and we are free to do so without fear because the path is safely distant. With the safety case made, the stage widens to a different kind of weather. Not solar wind or forward scattering, but headlines and social feeds. When a story mixes numbers with mystery, coverage can sprint ahead of the data. Claims can swell in the retelling. Sensible caution can be mistaken for evasion. The next part steps into that pressure system. We will trace how a careful preprint becomes a wild caption, how skepticism becomes entertainment, and how to carry a compass through the maze without losing the sense of wonder that began this chase. A quiet plot of residuals does not look like a headline. A forward glow that confuses intuition does. Between those two lies the maze where science becomes story. The path starts on a preprint server, where authors post analyses that invite rapid feedback. Journalists scan those pages for signals. Social accounts lift phrases, trim context, and add urgency. Somewhere in the journey, a careful limit on acceleration becomes a suggested mass. A suggested mass becomes a giant with a personality. A giant becomes a character in a drama about what we might have missed or what someone might be hiding. The maze feeds on speed. The science feeds on patience. Begin with how a claim grows legs. The original work speaks of a lower limit on mass, derived from the absence of a measurable non-gravitational push despite clear activity. The phrasing is cautious. The analysis is upfront about assumptions. Then a summary appears that trims the careful parts. Later, a headline chooses one number because a single number travels well. That number floats away from the caveats and the calibration checks. When readers finally meet the story, it arrives as a statement, rather than as a bound with conditions. The wonder is real. The nuance is missing. The cure is not to scold audiences for liking wonder. It is to put a small compass in their pocket. The compass has 4 points. What was measured? What was inferred? What would change the claim? What would not? Measured items are the positions of a point on the sky across many nights, the presence of a coma in images, and the signatures of water, carbon dioxide, and carbon monoxide in spectra. Inferred items are the lower limit on mass that follows from those positions, and from reasonable ranges for gas speed and production, and the grain sizes that forward scattering suggests. What would change the claim are new measurements that show bursts during the current blackout, or revised gas speeds and production rates that are far outside early estimates, or a strong detection of a non-gravitational acceleration as the arc lengthens. What would not are recycled rumors about artificial intent without supporting signatures, or single-frame images that ignore phase angle, or retroactive certainty in a story that is still being written. A second twist in the maze is the shape of skepticism. Real skepticism is a method. It asks how to break a claim. It proposes tests that could flip a conclusion. It listens when those tests are done. Performative skepticism is a costume. It treats uncertainty as a confession rather than as a normal stage in discovery. It prefers a tone of gotcha. The difference matters because the object at the center of this story is not fragile. It will still be there after a viral thread has cooled. The work will still be there to be checked. The tests will still be there to be done. The responsible stance is to keep the door open to revision while refusing to award victory to the loudest frame. There is also the gravitational pull of the extraordinary. People want a big reveal and a clean villain. They want either a natural giant that rewrites ejection models or a technological artifact that whispers across space. The truth may be in the middle. A heavy comet that behaves oddly because dust and gas conspire to redirect momentum. That middle is not dull. It is rich. It forces better modeling of Kamai. It asks for more. Multi-vantage campaigns. It encourages new pipelines that treat short-arc hyperbolas as high priority rather than as discardable glitches. It also leaves room for wonder because it ties the chemistry of alien ice to the physics of sunlight and to the choreography of grains in a vacuum. We can help the maze behave by setting simple expectations. Early numbers are scaffolds. They hold the work while more beams are added. Peer review is a stress test, not a ceremony. Independent reductions often find different edges on the same shape. When a result survives these steps, it graduates from interesting to sturdy. None of this dims the spectacle. It gives the spectacle a flaw. Audiences who understand the flaw enjoy the show without losing their footing. Reorientation of the through line. We are still weighing a breathing traveler, and we stay oriented by separating measurement from inference, while keeping our curiosity wide open. Now that we have cleaned our lenses, we can let speculation do useful work. If massive interstellar visitors have been crossing the dark for ages, what role could they play in building worlds? Some researchers have explored a graceful notion: captured travelers as seeds that jump-start planet growth by skipping the slowest stage. It is a what-if that links the mass question to a grander picture. The next part walks through that possibility with the same disciplined curiosity, and it asks whether alien chemistry carried by such seeds could leave a signature in skies that do not belong to us. Picture a young star with a gauzy disk, bright with dust and gas, busy with turbulence and slow collisions. In the classic story, grains kiss, stick, grow, and fall inward under drag. Growth stalls near meter sizes because drag pulls faster than gravity can gather. The meter barrier is the stubborn gate that every world must pass. One possibility is that some worlds cheat. They begin with refugees from interstellar space, large bodies that wander into a young disk and are captured by friction with gas. A captured body arrives already past the hard part. It resists drag, it stirs eddies, it eats. In a few 100,000 years, a seed can become a core. In a few million years, the core can drink gas and turn into a planet. The physics of capture has a quiet elegance. A traveler crosses a disk on a hyperbolic path and loses a little energy to the gas at every pass. If the star and the traveler meet while the disk is still thick, the traveler can shed enough speed to become bound. Once bound, it spirals inward as gas drag and gravitational torque steal angular momentum. The seed grows while it falls, collecting pebbles and planetesimals along a path that looks like an arm swept through fog. A competing view suggests that capture is most efficient for bodies that are already a kilometer or more across. They plow the gas rather than being plowed by it. That is why a heavy interstellar visitor matters for this idea. It is exactly the kind of body that a rich disk could keep. Evidence is limited, but one inference is that chemistry could betray this history. If a captured seed formed beyond the carbon dioxide snow line in a different system, it might carry volatile ratios that do not match the local disk. Later, as the planet grows, those fingerprints could appear in the atmospheres that telescopes read when they watch a world cross its star. A minority view holds that isotopic ratios would be the sharper tracer, though extracting such precision from exoplanet spectra remains a steep challenge. For now, the test is statistical. If more massive stars with richer disks host more giant planets at wide separations, capture may be part of the reason, since those disks offer thick air to slow an incoming seed. Turbulence can help capture rather than hurt it. Eddies increase path length inside the disk and raise the chance that a passing body will lose enough energy to stay. Spiral arms born from self-gravity can also collect seeds into lanes where drag works harder and feeding is faster. In that case, a single captured body might not stay single for long. It could shepherd pebbles, carve a gap, and set the stage for a second generation of planetesimals that grow in its wake. Simulations show such behavior in stylized cases. Reality is tangled. It remains uncertain whether capture can deliver seeds often enough to matter for the total population of known exoplanets. This visitor lets us aim the question at something we can touch with light. If bodies like it are common in interstellar space, and if they are as large as the current lower limits suggest, then capture becomes a natural partner of ordinary growth. If they are rare, then this path is a curiosity. Survey statistics will decide. The Rubin era can reveal how many travelers cross the inner sky each year and how their sizes stack. Pair that with models of star-forming regions where young disks live hip to hip, and capture rates can be estimated with fewer guesses. If those estimates line up with the frequency of giant planets in wide orbits, the idea gains traction. There is a deeper wonder here that deserves to be spoken without romance. Seeds that travel between stars would mix the chemistry of the galaxy. A core born under a red sun could end its days as a kernel for a planet under a white one. Organics locked in ice beyond one snowline could be warmed and transformed under another. The exchange would be slow and quiet yet grand in scale. It would turn planetary systems into members of a wider community of matter, where no disk is an island and where the map of a world includes histories that began far away. Critics of the seeding idea raise fair barriers. Captured bodies must survive tides near a young star. They must avoid quick ejection by newborn giants that are rearranging the system under them. They must not grind themselves to dust upon entry if relative speeds are high. Each of these hazards can be modelled. None has, yet killed the idea. The most honest position is patient. Let surveys measure the rate of large visitors. Let exoplanet demographics mature until the fingerprints of wide giants and their host stars are cleaner. Then ask whether capture adds a missing piece or simply paints a pretty picture that the numbers do not need. Reorientation of the through line. We are still weighing a breathing traveller, and now we have asked whether bodies like it might change how worlds begin. Before we accept a shortcut to planets, we should also give standard physics every chance to explain the present puzzle. Large mass is the tidy route, yet there are natural ways to lower the expected shove without invoking giants. The next part collects those conservative paths, trims the ones that fail to fit, and leaves on the table the few that could narrow the mystery while keeping the object in the realm of the ordinary. If the heavy answer is the cleanest, the conservative answer is to see how far ordinary physics can travel before it runs out of road. Begin with momentum coupling, the quiet hinge in the whole argument. Gas leaves the surface at a few hundred meters per second. Only a fraction of that escaping momentum becomes a net shove. The rest is wasted in turbulence, or balanced by flows on the opposite side, or spent lifting grains that do not carry thrust for long. Could that fraction be far smaller than assumed? It can, within limits. A crust of sintered dust can act like a sieve that dissipates energy. Vents can be so many and so widely spread that pushes cancel over a rotation. A layered surface can leak through cracks that aim in changing directions as shadows drift. All of these behaviors reduce the effective shove. None of them erase it entirely. That is why the mass flaw remains stubborn even when modelers turn the efficiency knob down. Next, turn to geometry. The path through the sky is measured by the brightness center, not by the hidden rock. If the coma is lopsided, the centroid can shift toward the sun or toward an active arc. Perhaps that shift is large enough to hide a gentle nudge or to mimic one. Observers know this trap. They try multiple apertures, track phase angle dependence, and compare visible with infrared maps that follow gas instead of dust. A systematic offset that moves with the forward lobe can be modelled and subtracted. What remains after that bookkeeping is still a curve that fits gravity as if it were the only force. Coma geometry complicates the accounting. It does not balance the ledger all by itself. A third path lowers the inputs on the other side of the equation. If production rates are smaller than early estimates, the expected thrust shrinks. If gas speeds are slower, the same happens. Evidence is limited, but one inference is that infrared line profiles already set a sensible floor on gas speed, and that the extended carbon dioxide coma implies non-trivial mass loss. Future spectra could still revise these numbers. If they fall, the mass limit will relax. For now, they do not appear low enough to transform a small body into a plausible solution. Another idea focuses on dust. A dust-rich coma brightens easily but carries little push if the grains are large. This is compatible with the persistent forward glow, since large grains scatter light into the sunward direction with enthusiasm. In such a case, the visible cocoon advertises more than it accelerates. The gas momentum may be partly invested in lifting heavy grains that then fall back in slow arcs. That creates a bright envelope that does not translate into a steady thrust. This path does not remove gas recoil, it makes the coma look louder than the mechanics under it. If you fold that into the efficiency term, the mass floor remains up, but the climb is not as steep as a naive reading of brightness would suggest. Survivorship and sample bias add a quiet background. Smaller interstellar fragments may have faded or fractured during long travel. Large bodies survive to cross our search fields. If the first bright visitors are more likely to be dust-rich and active at long range, then surveys will find them first. That makes the sample feel top-heavy, while quieter shards slide by in numbers we cannot yet measure. This path does not explain breath without shove. It explains why an apparent giant might arrive early in a short diary of discoveries. Rotation presents a final conservative lever. If jets are fixed on the surface and the nucleus spins, thrust directions change with period. Over many cycles, vectors cancel. If vents also migrate as sunlight warms and cools fissures, cancellation becomes even stronger. Analysts already include such behavior in simple forms by integrating activity over many hours. A rotation-like curve tied to photometric changes would let them do better. The Mars window and the near-Sun cameras can help by catching any periodic breath. If a robust period appears, and coma models tie the phase of that period to changes in brightness and centroid shift, then the momentum that survives after a rotation average could fall below earlier expectations. Even then, a clean gravity fit over months would remain a strong argument for mass. These natural paths share a virtue. They are testable. Polarization can sort grain sizes. Multiband astrometry can bracket the photocenter offset. High-resolution spectra can refine gas speeds. Time series photometry can reveal rotation and jet geometry. None of these tests need an extraordinary explanation. All of them sharpen the same picture. If they move the needle, the mass flaw will ease. If they do not, the heavy answer will harden. The story remains disciplined. We keep shaving away what normal physics can do, and we note what it cannot. That is the right posture before turning to the interpretation that captures imaginations and arguments in equal measure. A minority view proposes that silence in motion hides a controlled hand. To judge it fairly, we must ask what an engineered object would do that nature would not, and whether any of those signatures have appeared. There is a version of this story that arrives with a raised eyebrow. A body breathes yet does not budge. Its path threads the planetary plane with tidy geometry. Nickel sings while iron stays shy. A few voices ask the question that fiction asks on page 1. What if someone were steering? Responsible curiosity does not slam the door. It opens it a crack and shines a light inside. What would steering even look like? What signatures would separate intent from ice? What tests could welcome a bold claim or send it home? One possibility is sustained accelerations that refuse to care about heat. Sublimation lives on sunlight. Activity rises as the visitor warms and falls as it cools. A controlled hand would leave a different pattern, a steady push that begins at a time that does not match a heating curve, a change in speed that holds through daylight and darkness, a turn whose timing obeys a clock that no rotation can explain. Analysts can search for such behavior by fitting long arcs before and after perihelion with models that allow onsets and offsets at arbitrary dates. If the best fit forces a thrust that ignores distance from the sun, the door opens farther. If the best fit always settles near a solar-driven law, the door closes. A competing view suggests that intent would speak in the spectrum. It remains uncertain whether narrow radio tones would be visible above solar noise at these distances. Yet coherent signals are a crisp test. A tight line that tracks the object across the sky and repeats in a pattern that lands on predicted schedules would be hard to blame on plasma weather. Optical and infrared light can also carry engineered fingerprints. A bidirectional reflectance function with sharp features that repeat at fixed angles independent of phase would hint at surfaces that were tailored rather than born. A thermal map that stays flat across day and night with a precision that rotation cannot justify would hint at interior power. These are not easy measurements. They are standards to reach for if the minority view is to be taken seriously. Evidence is limited, but one inference is that geometry will be the first temptation. Orbits that pass behind the sun from Earth look like evasive maneuvers in casual telling. They are not. The path is a straight story written by gravity and entry speed. A minority view holds that low inclination is suspicious because it lines up with the plane where our telescopes stare most. Critics answer that our surveys are biased toward that plane as well. Selection can make coincidence look like intent. The cure is not rhetoric. The cure is counting. As the sample of interstellar visitors grows, we will learn whether gentle inclinations are common or rare. Another place to seek intent is in the near field of the coma. A craft would disturb the plasma in ways that are not simple to fake with jets. A magnetometer that saw stable field structures stuck to the body through changes in lighting would raise eyebrows. A particle detector that counted electrons and ions in ratios that suggested active shaping rather than passive photoionization would do the same. These are measurements that require a neighbor. Without a flyby, they remain wishes. With a distant past, they become possible if not easy. Time protects us from wishful thinking. A single odd night can be a software error or a glittering coincidence. A repeated oddity that arrives when and how you said it would counts for more. That is why teams who entertain the minority view also publish predictions. If an unusual acceleration begins after the blackout and grows to a particular value, it should change the track in ways that precise astrometry can catch. If a radio tone exists, it should drift in frequency as the motion along the line of sight changes with predicted sign. If nothing appears when and where it should, the view retreats in order to survive. There is also the burden of parsimony. Every extraordinary hypothesis must beat a natural one on economy of assumptions. Breath without shove is already surprising. A heavy nucleus and tricky dust can explain it with ingredients we know from other comets. An engineered vehicle must explain why it wears a coma at all, why it follows a gravity-set hyperbola, and why its supposed actions track solar heating better than a power budget would demand. Sensational answers should not feel like excuses that keep changing shape. In public, words matter as much as measurements. It is easy to tell a tale that sells mystery by promising what no instrument has yet seen. It is harder and more honest to say that a minority view exists and that it has clear, testable criteria. That is the correct posture here. A controlled hand would leave signatures in motion that ignore heat, in light that repeats like a clock, and in plasma that holds patterns no jet can sustain. So far, the ledger holds gravity, sunlight, dust, and gas, and no signal that refuses to live under those laws. Reorientation of the through line. We are still weighing a breathing traveler, and every wildcard is judged by whether it makes testable promises that nature cannot keep. The next part brings the focus back to the craft of watching. Perihelion is behind us. The object swings outward into kinder skies. This is when long patience pays off. A clean post-solar arc can confirm or soften the mass flaw. It can check rotation against jet maps. It can show whether the forward glow fades as the geometry unwinds. The plan is not glamorous. It is the slow work that decides how this paradox ends. Perihelion has passed, and the glare thins. The visitor settles into colder light, and the sky around it darkens back to black. This is the quiet season when spectacle gives way to the work that decides what remains in the ledger. Outgassing should relax. Water should yield slowly to the colder breath of carbon dioxide and carbon monoxide. The coma should contract. Forward scattering should weaken as phase angles grow. If the paradox was an illusion born of geometry or a lucky run of cancellation, it will fade with the coma. If the paradox was real, the orbit will continue to sit inside the rails laid by gravity, with only the tiniest tremor from the jets. The plan begins with cadence. Observatories resume their relay and rebuild the chain of positions night by night. Early sessions prioritize reference fields with well-calibrated stars to re-anchor the astrometric solution. Teams repeat the aperture tests that measure how much the photocenter drifts when the inner coma brightens or dims. They pair each position with a light point so that any small centroid shift can be read in the context of a change in brightness. This coupling of motion and light is the core habit that keeps tiny accelerations honest. It was important before the Sunday. It is essential after. Photometry now plays a second role beyond context. If rotation modulates activity, the light curve can uncover it when geometry is friendlier and when daily interference from glare is gone. A slowly repeating rise and fall hints at a spin period. That period, tied to changes in color or polarization, can map jets to faces on the nucleus. Once a map exists, analysts can predict how thrust should cancel over many cycles. If predicted cancellation is strong, then a small residual push might fall below detection. If predicted cancellation is weak, then the lack of a measured push becomes sharper evidence for a heavy body. Spectroscopy returns with better leverage as well. Water lines should soften, carbon dioxide may linger, carbon monoxide may drift toward dominance. The ratios tell a thermal story that either smooths or complicates the modeling of momentum. A smooth story favors simple sublimation that scales with distance. A complicated story favors vents and layers that produce uneven, outflow. Either result is valuable. The first strengthens the clean inference of mass from a persistent lack of recoil. The second sharpens the assumptions in momentum efficiency and could, if extreme, lower the mass floor. Watching the nickel lines again belongs on the list. If they fade in step with dust indices, then photodesorption on grains was likely responsible. If they hold while other traces fall, then release processes operate farther from the nucleus and feed the gas even as the core cools. Morphology should evolve. The sunward glow will relax as phase angles climb and as large grains drift out of the inner zone. The classical antisolar tail may become more prominent while the inner lantern dims. This change is not cosmetic. It reduces the sunward bias on the photocenter and lets the orbit depend less on model-based corrections. Astrometrists cherish such stretches because every reduction in photometric complication translates into tighter bounds on any non-gravitational term. If the fit still refuses extra acceleration in this cleaner geometry, confidence in the mass limit rises by more than the word limit can express. None of this work ignores hazards. Weather still steals nights. Instruments still behave like personalities that must be coaxed into predictability. The object grows fainter as it recedes, so exposure times stretch and the field stars thin. Teams respond with strategy rather than drama. They coordinate to stack short exposures into deeper frames. They share calibration stars to keep plate solutions consistent. They schedule larger mirrors to touch the target once each week, then ask smaller arrays to fill the gaps. Each choice pushes uncertainty down one more step. There is a special prize that a long post-perihelion arc can offer, closure on the fear that a hidden outburst tipped the balance during the glare. If the orbit on the far side matches the gravity-only prediction from the near side within the stated uncertainties, then any unobserved shove was too small to matter for the lower limit. That comparison is the nearest thing to a courtroom verdict that this kind of story ever gets. It is not a headline. It is a quiet check that lets the rest of the analysis stand without an asterisk. The long arc also prepares the field for a future flood. Pipelines that track this object through fading light will be the same engines that follow the next 100 interstellar visitors. Methods honed here will become defaults: aperture bracketing, phase angle sweeps, multiband centroids, polarization as a routine, not an exception. The paradox of breath without shove may end as a validation of those methods as much as a statement about this one body. And if the paradox survives the long arc, the story will be ready for its final turns, where we look at what this visitor has already changed and what it will leave behind when it slips back into the dark. Some visitors depart and leave only a pretty picture. This one has already rearranged desks. The first change is methodological. Astrometry for active bodies becomes a two-language exercise everywhere, motion and light in the same breath. Aperture bracketing will graduate from best practice to basic requirement. Phase angle sweeps will be scheduled as if they were calibrations rather than extras. Multiband centroids, visible paired with infrared, will be the norm. Polarimetry will slide from a niche specialty to a standard column in proposals. The reason is not fashion. The reason is a paradox that could only be weighed with instruments that listen to brightness and gravity at the same time and refuse to let one lie for the other. The second change is statistical. Discovery programs will adjust search latitude and cadence because finding an apparent elephant early reminds you that mice can be shy. Pipelines will learn to flag short arc hyperbolas with higher priority and to keep them in the queue long enough for follow-up to matter. Survey teams will tune their filters to identify comae at longer heliocentric distances, since cold-driven chemistry can wake far from the Sunday. Rubin will do most of this automatically with depth and cadence, but the lesson runs beyond one observatory. A distributed network that shares templates for photometric and astrometric joint fits will turn the world into a cleaner single instrument than it was when this story began. The third change lives in models. Momentum coupling in comae will get the attention it has always deserved but rarely received. Efficiency will stop being a single slider and start being a field that maps to vent geometry, dust size distributions, and rotation state. Morphology corrections will move from hand-tuned recipes to forward models that generate photocenter offsets as a function of phase angle, color, and polarization. Chemistry suites will treat carbon dioxide-driven regimes as first class rather than as footnotes to water. These changes do not flatten the mystery, they give it edges. A field that can create a mass floor from silence and acceleration should also be able to bound how much of that silence is geometry and how much is true heft. A fourth change is cultural. The maze between preprint and headline gains a new map. Reporters and readers who followed this story learned to ask four simple questions. What was measured? What was inferred? What test could change the claim? What would not? That habit, if it lasts, will protect fragile claims without smothering wonder. It will also make the spectacular easier to enjoy, because it will arrive with scaffolding that does not wobble. Wonder needs a floor as much as a ceiling. Reorientation of the through line. We are still weighing a breathing traveller, and now we can see the tools that will weigh the next 100 without losing the plot. The fifth change looks outward toward formation theory. If the lower bound on size continues to hold, ejection models will be forced to make room for rare but robust launches of heavy bodies from cold reservoirs, and to consider how cluster environments pump probabilities for such launches far above single-star expectations. Capture as a planet seeding pathway will not graduate on the strength of one object, yet it will move from curiosity to testable framework. Simulations will couple cluster dynamics to disk drag in ways that predict not just rates, but size distributions for captured seeds. Exoplanet demographics will offer the scoreboard. None of these shifts require a final verdict about this one visitor. They are the fruits of disciplined ambiguity. The object breathed, its path stayed clean. The forward glow persisted in a way that demanded grain physics. Nickel sang in the spectra, while iron stayed quiet, which forced a chemical investigation that is still running. Mars will have watched from the side balcony. Inner solar cameras will have softened the blackout. The long post-perihelion arc will knit the story into one curve. Wherever the mass floor finally sits, the community has already changed its posture. It is now ready to weigh paradoxes, instead of arguing about whether paradoxes are allowed. There is also a human change that is harder to plot but easy to feel. Students who watch the world act like one telescope saw patience win. Teams that rarely speak to each other shared calibration stars and phase angle plans. Amateur observers became crucial links in a chain that measured an absence with the same care usually reserved for bright fireworks. That ethic will outlast this glow. The next visitor will arrive into a culture that knows how to honor wonder without feeding confusion. What remains for this script is a goodbye that keeps its eyes open. The object will fade, the ledger will close, and the papers will settle into place. The final part does not promise revelation. It promises a vantage that makes room for both answers we can prove and questions we are now smart enough to ask. The silent giant will leave, but the way it taught us to listen will stay. Night returns to the domes, and the relay begins again. The visitor drifts outward, fainter now, its lantern shrinking, its breath less visible against the stars. What remains is not silence. It is a ledger that became a mirror. We weighed a body by the push it refused to show. We mapped a glow that pointed toward the sun and learned it was light, choosing a path through grains, not dust falling uphill. We read chemistry that smelled of deep, cold carbon dioxide rich and early to wake, and we set that smell beside a motion that stayed austere. The paradox never asked us to shout. It asked us to listen with care. The gift of this traveller is a new habit of mind. We learn to pair every dot on a starfield with a brightness context, and to treat a photocenter as a moving target that can be coaxed into truth but never bullied. We learn to hold a flaw with quiet pride, to say lower limit without apology, and to let that flaw guide models rather than pretend to know the ceiling. We learn to let Mars speak when Earth could not, and to trust cameras that live near the sun to stitch the blackout into a continuous film. We learn to be honest about what a comet does when it breathes. That vapor is a violin whose note can be loud in light and soft in motion at the same time. There is a softer lesson that hides in the work. Wonder can be disciplined without being dimmed. A forward glow can still feel eerie after you have written the math of scattering. Nickel can still sound surprising after you have listed the natural ways it might leave a grain. A world acting as one telescope can still look like a miracle, even when you know the names of every plate solution and every clock. The mood of this story began with mystery, then moved through tests, then returned to mystery in a kinder shape. The unknown did not shrink. It became a landscape with paths. Our through line remains intact. A breathing traveller stayed, nearly true to gravity. The ledger of momentum balanced only when we set a heavy body on one plate, or when we allowed efficiency to fall in ways that the chemistry and images could tolerate. That is not a final verdict. It is a corridor that narrows wild claims and invites sober ones. The corridor leaves room for future visitors that will land on other squares of the chart. A small shard that drifts without a coma, a bright cloud that twitches under the Sunday, a slow giant that barely wakes and still writes a whisper into the orbit. We are better prepared for all of them. Speculation keeps a seat at the table, but it keeps a promise as well. One possibility is that captured seeds help some young disks cheat the meter barrier. A competing view suggests that cluster flybys and rare chains of kicks alone can throw giants into the dark. It remains uncertain whether survivorship trims the small more than we guessed during million-year journeys. Evidence is limited, but one inference is that the coming surveys will decide faster than we expect. The test is to count and to sort, not to wish. When numbers come, debate becomes design. In the end, the most cinematic image is not the teardrop coma or the ghostly halo on an infrared map. It is the planet itself as an instrument, time zones, handing the baton across oceans, amateurs and professionals, sharing stars, old spacecraft, turning slightly to gather a few photons for a puzzle they were never built to solve. The spectacle is not only out there, it is in the choreography that made an absence into a measure. The visitor will fade beyond ready reach. The ledger will close with more margins than some would like, and fewer than many feared. Papers will slow from preprints into print, and from print into textbooks that will already feel a little out of date by the time the next messenger arrives. What stays are the rules we wrote together. Separate measurement from inference. Keep the known beside the unknown. Ask for a test that could change your mind. Enjoy the awe you have earned. A last look then. A point of light slides through a dark field, less insistent than before, still moving as gravity intends. It carries the weather of another sky in its ices. It leaves behind a craft we did not possess when it appeared. If there is a legacy worth keeping, it is that we are now better at listening to subtle things. The universe has more of those than it has of trumpets. The silent giant taught us to hear them.